So, we will continue our discussion on this von Karman energy integral equation, and that is an alternative to this normal this energy equation, then this continuity equation and the Navier-Stokes equation combined. So, if you solve, we have discussed it in the previous session, that if you solve you can get this u, v and t, right, but that is the solution equivalent to the solution of 3 second order, 1 first order and 2 second order PDEs simultaneously, which is definitely complicated in terms of its mathematical integracy. So, here just like the Blasius solution, the alternative to Blasius solution was this von Karman equation, right, von Karman momentum integral equation. Here we are going to write simply and discuss about the von Karman energy integral equation. So, von Karman energy integral equation I am not going to prove, just I will write the form and we will discuss how to use it. So, von Karman energy integral equation for thermal boundary layer. So, what is that? It states that ddx integral 0 to delta t u t minus t infinity minus alpha del t del y at y equal to 0. So, structurally you see it has got similarity with this momentum integral equation, which states this 0 to delta, then u by capital U 1 minus small u by capital U, here definitely it is dy, it is equal to tau w is mu into del u del y at y is equal to 0 divided by rho into u infinity square. So, here u infinity and here u infinity. So, you see that further if I simplify the form, so ddx 0 to delta u into u infinity minus u dy nu into del u del y at y equal to 0. So, you see structurally it is very similar, right, these two forms. So, ddx and ddx here u is the velocity, right, this is the primary and fundamental quantity, this u, and here it is thermal boundary layer. So, this is local property minus free stream property. So, actually if we change this this as small u minus u infinity, you will have a minus sign here. So, local property minus free stream property integral over this y, right, here minus alpha the thermal diffusivity, here momentum diffusivity, del t del y at y equal to 0, here del u del y at y equal to 0. So, structurally they are very similar, but one here this local property, this is a local property, difference of this local property and the free stream property. This is velocity because it is momentum integral, here it is this thermal boundary layer. So, it is the thermal integral, this energy integral equation. So, how to use it? Very similar. What we did here, where we have used, we considered that u by u infinity was equal to a0 plus a1 y by delta plus a2 y by delta whole square plus a3 y by delta cube, right. And we have solved it considering the boundary condition at y equal to 0, u equal to 0 and del square u del y square is equal to 0 and y equal to delta u is equal to u infinity and del u del y equal to 0, right. So, you have got that solution, that small u by capital U infinity as 3 by 2 y by delta minus half y by delta whole square. So, that we have substituted here and we have written tau w. So, we will finally get a differential equation in the form of delta, which we have solved to get delta as a function of x. So once delta as a function of x is obtained, my velocity field is actually solved, right? So here it is temperature. So very similar to velocity, we consider a polynomial to represent this. So t minus Ts and here T infinity minus Ts. There is an error in the handout, a typo. So you change it, it should be T minus Ts divided by T infinity minus Ts. So what does it mean? You see here u minus 0, 0 is the velocity at the plate, divided by free stream property minus plate property. But here the plate property for case of temperature, it is not equal to 0. So T minus Ts divided by T infinity minus Ts. And we consider it to be equal to B naught plus B1 y by delta T plus B2 y by delta T square plus B3 y by delta T cube. Right. And what are the conditions? Boundary conditions. Y equal to 0, T equal to Ts, del square T, del Y square 0. Why? Because from the general energy equation we know that U del T del X plus V del T del Y is equal to alpha del square T del Y square. At Y is equal to 0, U equal to V equal to 0, so del square T del Y square is also 0. Right? Number 2, actually there are 2, 1 and 2 we can write is this, and 3 and 4 we can write that Y is equal to delta T, T is equal to T infinity and del T del Y equal to 0. So if you solve, you will get the same type of this parabolic polynomial, parabolic or quadratic equation, which is T minus Ts divided by T infinity minus Ts to be equal to 3 by 2 y by delta T minus half y by delta T cube, right? Now let chi, we write it, y by delta T, sorry, zeta y by delta T and chi, which is delta T by delta. So y by delta is equal to chi into zeta. Right. So if I substitute it here, so we get that d dx integral will be from 0 to 1, u is u infinity within bracket this velocity field, that is 3 by 2 chi into zeta minus half chi into zeta cube, right. Next we have a term T minus T infinity. You see T minus T infinity is equal to this T infinity minus Ts, or rather T minus T infinity, how we can write? We can write T minus Ts divided by T infinity minus Ts minus 1. That multiplied by T infinity minus Ts. Now T minus Ts divided by T infinity minus Ts already we have solved. So this is minus 1 plus 3 by 2 y by delta T minus half y by delta T cube into T infinity minus Ts. Now dy is d zeta into delta T. So it is delta T into d zeta. And on this side we have minus alpha into del T del Y. So minus alpha, keep it as it is. Now del T del Y, here we have del T del Y is equal to this T infinity minus Ts, it will be multiplied, and then the derivative of it. So here this quantity is this. So if you take the derivative 3 by 2 y delta T, and here will be y square, and at y equal to 0, this part cancels out. So it will be 3 divided by 2 delta T. Now this and this cancels out from two sides, right? And if I include alpha, this minus and here this minus, we can go for d dx 0 to 1. Now, u infinity we can take out. This delta t we can write as chi into delta. So, here delta will be there, chi will be there. Inside we will have 3 by 2 chi into zeta minus half chi into zeta cube into 1 minus 3 by 2. This minus sign will change here, minus we can extract out. So, 1 minus 3 by 2 y by delta t plus half y by delta t, you see it is zeta itself and here it will be plus half zeta cube d zeta is equal to 3 alpha divided by 2 into, here we can further write this delta t as chi into delta, right. So, this equation we have to integrate basically. This part we have to integrate with respect to zeta and chi remains constant. So, under this condition it will be giving you that this will give you, after this algebraic simplification, u infinity d dx, u infinity d dx. I am not doing the intermediate algebra, it is bit complicated and it's simple integration. So, it is basically we can leave it, right, minus 3 divided by 280 chi to the power 4 and that is equal to 3 alpha divided by 2 chi delta, right. So, that here we have reached here. Next, the point is, you see, if I keep this as it is, it's difficult to proceed further, right. So, we have to do something in order to simplify this. So, what von Karman did, he mentioned that here this chi is delta t by delta. Definitely it is smaller than 1 because we have assumed that a thermal boundary layer is well within the hydrodynamic boundary layer. So, delta t is less than delta. So, as delta t is less than delta, chi is less than 1. So, chi to the power 4 is much smaller than chi square. So, it dropped the second term and got this expression that u infinity into d dx of 3 by 20 chi square into delta, 3 by 20 chi square into delta is equal to 3 alpha divided by 2 chi delta. So, this 3 cancels out, 20 and 2 cancels out, giving a 10 here, right. So, d dx of chi square into delta is equal to 10 alpha divided by chi into delta into u infinity. Now, if I break it down, I will get d delta dx into chi square plus delta into d dx of chi square is equal to 10 alpha divided by chi delta u infinity. Got it? So, you see this Blasius solution gives this delta is equal to 4.64 into x divided by under root Rex, right. So, d delta dx is equal to 4.64 and actually here Rex, if I break it down, u by eta whole to the power half and this is x to the power half. So, half into 1 divided by under root x. So that if I just combine it, so 4.64 into x divided by root over of Rex, then we will have 1 by 2x. So it is delta divided by 2x, right? So delta divided by 2x into chi square plus delta into d chi square dx, right? Or rather we can write 2 delta into chi into d chi dx equal to 10 alpha divided by chi into delta into u infinity, correct? So the thing is, if I cross multiply chi, 2x here chi cube plus 2 delta into chi squared d chi dx equal to 10 alpha divided by delta into u infinity. So you see this ddx of chi cube. So if I write here ddx of chi cube is equal to 3 chi square d chi dx. So we have chi square into 3 this, so it is 1/3. So we'll have delta divided by 2x chi cube plus 2 by 3 delta into ddx of chi cube is equal to 10 alpha divided by delta into u infinity, correct? So now if I divide this entire equation by 2/3 of delta, so I will get d chi cube dx plus delta divided by 2x 2/3 delta into chi cube is equal to 10 alpha divided by delta into u infinity and 1 divided by 2/3 delta, right? So here d chi cube dx plus this 3 by 4 x chi cube is equal to this will be 2 5, so 15, yeah, it will be 15 into alpha into delta square u infinity, right? So yes, this is 3 by 2, 15. So 15 into alpha divided by delta square is 4.64 square into this and there will be x, of course, 2/3 delta, right? 2/3 delta we have multiplied, 4.64 square into x square divided by u by nu, right? U infinity by nu, and that is also multiplied by u infinity. So this u infinity cancels out. So u infinity cancels out, and the modified form is you see it will be something like this. D chi cube dx plus 3 divided by 4x chi cube is equal to 15 divided by 4.64 square, and x, there will be x also, so x square, because it's 4.64 x square divided by under root will go off upon squaring, it will be Rex only. So, which is ux into u infinity by nu. So, this 4.64 alpha by nu into 1 by x. So, that is 15 divided by 4.64 square 1 by Prandtl number into 1 by x, and let us say this chi cube is equal to some whatever eta. So, d eta dx plus 4 by 3x into eta equal to this. So, integrating factor of this equation, it will be e to the power integral 4 by 3x dx, right, e to the power 4/3 ln x. So, e to the power ln of x to the power 4 by 3, sorry, that is 3 by 4, 3 by 4, 3 by 4. So, it is 3 divided by 4, here also 3 by 4, x to the power 3 by 4. So, it is x to the power 3 by 4, that is the integrating factor. So, d dx of eta into x to the power 3 by 4 is equal to 15 divided by 4.64 square into 1 by Prandtl number into x to the power 3 by 4 here. So, x to the power half this 1 by 4 here, x to the power 1 by 4 here. So, if you integrate, it will be eta into x to the power 3 by 4 is equal to 15 4.64 into 1 by Prandtl number, the x to the power minus 1 by 4, integral will be x to the power 3 by 4 divided by 3 by 4 plus C1. So, eta, which is 15 by 4.64 square into 4 by 3 into 1 by Prandtl number, then x to the power 3 by 4 cancels out, and C1 into x to the power minus 3 by 4, right. Now, at x is equal to 0, you see x is equal to 0, this xi, this chi equal to delta t by delta, right. So, that cube of chi is eta. So, eta must be 0 at x is equal to 0, right. Eta must be 0 at x is equal to 0. So, C1 is equal to 0, and once C1 is equal to 0, this eta, which is chi cube, and that is delta t by delta whole cube, is equal to 15 into 4 divided by 3 into 4.64 into 1 by Prandtl number, and actually it will come to be 13 by 14 if I am not wrong. Yes, it is 13 by 14. Yeah, it's 13 by 14 into 1 by Prandtl number. So, delta t by delta is equal to 13 by 14 into 1 by Prandtl number whole to the power 1/3. So, this is the exact relation between delta t and delta. So, once delta, you see delta we know as 4.64 into x divided by under root of Rex. So, we got delta t, and we can solve now for this Hx. So, how we can solve it? So, you see this yes, del t del y at y is equal to 0 is basically what we have written here, t minus Ts divided by T infinity minus Ts is 3 by 2 y by delta t minus half y by delta t whole cube, right. So, del T del y at y is equal to 0 is T infinity minus Ts into 3 by 2 delta T. Right. So, minus of Kf is equal to Kf into Ts minus T infinity into 3 by 2 delta T. So, that is obvious, we have changed the sign in order to accommodate that minus, and that must be equal to Hx into Ts minus T infinity. Right. That must be equal to Hx into Ts minus T infinity. So, Hx divided by Kf is equal to 3 divided by 2 delta T. Hx divided by Kf is equal to 3 divided by 2 delta T, and that is equal to 3 divided by 2 and delta T 1 divided by 13 by 14 into Prandtl number to the power 1/3 delta T multiplied by delta, and delta is equal to 4.64 into x divided by Rex to the power half. Right. So, immediately if I solve for the numerical constants, we will get this x, we will cross multiply Hx into x divided by Kf, which is local Nusselt number, will be giving you 0.323 into Rex to the power half into Prandtl number to the power 1/3. That is the dimensionless correlation we can obtain from one carbon, but actually you see that is the prediction of one carbon. So, the actual solution, which is obviously the combined solution of three differential equations, continuity, Navier-Stokes and energy balance. So, that will give you NUX is equal to 0.332 into Rex to the power half into Prandtl number to the power 1/3. So, error is less than 10%, right, which is, but here we have to go for this part numerical solution, because analytically it is not entirely possible, because as we know that Blasius solution is finally it is numerical solution, whereby similarity we reduce it to a third order nonlinear differential equation, and from there we have to go for this numerical solution in order to predict this delta to be equal to 5x divided by under root of Rex. But von Karman gives you an analytical solution. So, this is the difference, and here again the error is less than 10% as obvious. Okay. So, von Karman and this prediction is quite satisfactory. However, the point is that even for a simple geometry like a flat plate, you see that there is a tremendous complexity, we have to go for it, right, and even this is an approximate solution. It is a tremendous mathematical complexity, and finally we have derived that. So, we have to see of cases where we can have flow separations, just like see here if we think of situations like laminar boundary layer flow and there is flow separations here, right. And we know for 3D geometries, whenever we have standard velocity, except it is a Stokes law regime, right, 3D geometry is something like this, and there will be flow separation of course, where we will have the wakes and all, right. So, it is as this is impossible to predict temperature as a function of space coordinate. It is not possible, right. So, as it is not possible, what we have to go for then? Definitely we have to rely on experimental results of that specific geometry, and we can generalize it using the dimensional analysis. So, this entire derivation, though, and this entire analysis, whatever we have discussed, right, though it is simply giving you an analytical solution for flow over a flat plate in laminar regime, however, that corresponding equation, what is the outcome, and that is usable finally in real situation. That outcome is the energy equation, right? So, actually this energy equation coupled with Navier-Stokes equation and this continuity equation, if properly averaged for turbulent flow, can give you the temperature distribution, and here from computationally we can predict the heat transfer coefficient. But definitely we are not going into that because it is beyond the scope of undergrad, right. But that is the background. See, there are different models like RANS we have discussed, Reynolds average Navier-Stokes equation. So, RANS, continuity, average continuity, and similarly if I average the Navier-Stokes equation, the general energy equation, we will get the equation by which, by solving which we can predict the temperature distribution over any object, right. Whether there is flow separation or not, any geometry, it can be predicted, right. And it has been predicted, and these actually are the codes which run in the background of different these packages like COMSOL multiphysics or Fluent, right. These are all numerical CFD or these packages for transport processes. So, next the point is, before we go for the working dimensionless equation, right, we have to know the collection of dimensionless numbers. Just I am not writing the first, the Reynolds number we all know HL by K, wall temperature gradient divided by the temperature gradient across the fluid. Reynolds number we know, Prandtl number we have discussed. However, there are certain other numbers like Stanton number. ST Stanton number, which is H divided by rho Cp V bar, right. So, what is that basically? So, you can write it as H into this area, right, L square into delta T divided by rho Cp V bar into delta T into L square. So, what does it mean? Heat transfer by convection divided by heat transfer by bulk flow, right. Bulk flow and convections, they are actually different. You see, if this is solid and liquid and the solid is heated, liquid may be flowing in this direction, right. This is convection, okay, in the direction perpendicular to it. However, if I think that okay, certain part or over a certain region I have a heater and the liquid is flowing, so here temperature whenever it rises, it is basically the heat transport by bulk flow in the same direction as that of motion, okay. So, so definitely in the bulk flow heat transfer term, the velocity must be associated, right. So, you see that V bar into L square into rho, it is basically the mass flow rate into Cp into delta T, that is the enthalpy change, right, the change of enthalpy per unit mass. So, this is the heat transport by bulk flow, and numerator H into L square, the area into delta T, definitely the convective transport. So, that is the Stanton number. Peclet number is Reynolds number into Prandtl number. So, what it gives? So, D or L V bar rho by mu into Cp mu by K, right. So, L V bar rho Cp divided by K. So, and further from here we can write that this is rho Cp L square V bar into delta T divided by K into delta T L by L square. correct? Yeah. So then it will be giving you L in the numerator, right? So this is heat transfer or rate of heat transfer by bulk flow or heat transport by bulk flow divided by heat transfer by conduction, right? So that's the Peclet number. So similarly, we can have Graetz number, which is actually important for this, or which is very similar to Peclet number, but important in laminar flow. It is d by L. So Peclet number multiplied by d by L will be giving you the Graetz number, right? Now, what is the most common system we deal in, or geometry we deal in process engineering, and that is basically flow through a pipe, right? Because think of flow through a pipe or tube, think of heat exchanger, think of boilers, where everywhere we have heat transfer to or from a pipe, right? So that equation, flow through pipe, that equation is called this, the original equation was Debasish-Sarkar equation, and it states that H, average heat transfer coefficient, into D divided by K 0.023 into Reynolds number to the power 0.8 into Prandtl number to the power n, right? So n is equal to 0.4 for heating and n is equal to 0.3 for cooling. The equation is valid for Reynolds number high turbulence, Reynolds number greater than 10 to the power 4. The Prandtl number range is 160 to 0.7 and d by L must be less than 0.1, right? Okay. So that's the Debasish-Sarkar correlation. Now this equation has got a disadvantage basically because of n. So why the Prandtl number actually changes, that has been identified by Cedar and Tuttle. So what they have included additionally, that you see that during heating and cooling, what is the difference? Actually, when it is heating, the temperature profile will be something like this, right? High temperature and the bulk temperature will be lower. So this is the case for heating. And another case will be for cooling, where here the temperature is low, centrally the temperature is high. So it is TW and this is bulk. So this is cooling. And they found that these two cases, this Prandtl number is changing. Now the question, the introspection reveals that whenever there is the difference, change of this heat transfer process from heating to cooling, actually we have a change in the viscosity ratio of the bulk to that of wall. So they included this mu by mu W term, right? And from there they have got HD by K, the slight change of this heat, this constant 0.027, Reynolds number to the power 8, Prandtl number to the power 1/3 into mu by mu W whole to the power 0.14. That's the viscosity correction factor, right? We can alternatively write this entire group as phi of u. So this equation, the Cedar-Tuttle equation, this is valid for Reynolds number greater than 10 to the power 4. The Prandtl number range abruptly increases on the higher side, 16,700 to 0.7, right? And d by L is again less than 0.1. So that's the validity range for Cedar-Tuttle. Everything else remains same except the Prandtl number higher side value, several fold it increases, right? So up to air or gases, we can apply the Cedar-Tuttle equation. However, where the Cedar Tate or Ditas Bolter are not applicable for liquid metals, right. So, for liquid metals we have a different equation. So, that is not a standard, you do not have to remember it. So, if any problem is given in gate, so that for with liquid metal it will be specifically supplied. Now, you see at this point it is very important to understand the again this concept of equivalent diameter, because we will see later if I go for a double pipe heat exchanger, right. Just here double pipe heat exchanger structure, I am just describing it in an elementary form. This is the double pipe heat exchanger. Say here a hot fluid or hot fluid is flowing through the central pipe, and here we have the cold fluid moving in a countercurrent direction. So, cold in and here cold out, right, and this is the central pipe, this is the annular region. So, in order to calculate, we will see how it will be calculated. In order to calculate the overall heat transfer rate, right, we must know HI and HO, that is heat transfer coefficient inside, and this is heat transfer coefficient outside, right, and both may be in the turbulent flow regime. So, for HI we can directly apply this Cedar Tate equation, but for HO it is flowing through an annulus. So, we have to introduce the concept of equivalent diameter, right. Now, equivalent diameter, just this dE thermal, I think I have written as dE thermal, right, yes, dE pressure drop calculation and heat transfer calculation. So, dE thermal or DET, let us say DET, right, 4 into just like the hydraulic one, weighted area by weighted perimeter, and this weighted area and area will be same, but weighted perimeter may change, just I am explaining it. See here this diameter, let us say the outer diameter is D1 and here the inner diameter is D2, right. So, DET and the outside it is insulated totally, this is insulated. So, there is heat transfer only here, but there is no such heat transfer over the outer perimeter, right. So, weighted area will be pi by 4, D2 square minus D1 square, it is fine, but weighted perimeter will be only pi D1, not pi D2, right, because thermally that perimeter is not participating. However, for pressure drop calculation, it will be 4 into pi by 4 D2 square minus D1 square divided by pi into D1 plus D2, right. We can go for further simplifications and all. So, equivalent area, thermal equivalent area and hydraulic equivalent area, they may be different, that depends on the geometry. So, once you know this equivalent area, you have to find out the Reynolds number as dE thermal into rho into V bar divided by mu, right. Now, V bar here will be Q divided by pi by 4, it should not be pi this 4 into d square, it should be the actual cross sectional area, right. So, you calculate V bar, you calculate Reynolds number, check whether this Reynolds number is greater than 10 to the power 4 and then apply this general Cedar Tate equation. Now, for standard calculations in solving problems, right. So, we do not have to consider this phi u, we can take it in most of the cases to be equal to 1. But for actual design, definitely we have to consider it, and fluid properties you see, they are to be evaluated at this average temperature, some average temperature. So, there are different customs of averaging, I am not going into the detail. So, That's the flow through non-circular duct. Now for flow over a flat plate, already we have discussed. This is a pipe flow. For pipe flow, it is the Siddharth-Tate equation, right? And Siddharth-Tate equation can also be equivalently applied for this annular region. Now for pipe flow, flow over flat plate, for flow over flat plate, where we have analytical solution, Rex less than 5 into 10 to the power 5 laminar flow, right. So here NUX is equal to 0.332 into Rex to the power half into Prandtl number to the power 1/3. So if I average it out, I will get H bar, you see, as 1 divided by this L 0 to L H into dx, right, Hx into dx, right, because this is simply an outcome of H bar, the first formula whatever we have discussed, 1 by A H into d area average over A, because for a flat plate, if it has got a width W and length L, right, H is varying along X. So we consider this strip, right, the strip has got an area W dx. So 1 divided by W into L, total area 0 to L H into W dx, obviously giving you 1 by L 0 to L H dx. So that we are using here, and if I use it, integrate over the entire length of the plate, provided at the end point also, that is REL here. REL at the end point also we have laminar flow condition prevailing, then we have NU average is equal to 0.664 into REL to the power half into Prandtl number to the power 1/3, right. So if the flow is for turbulent boundary layer, that is Rex greater than 10 to the power 9, this you do not have to remember, you remember only this and Siddharth-Tate and Debasish. Debasish is not usable, basically Siddharth-Tate we majorly use, right. So this what I am going to write for turbulent flow, you do not have to remember, basically you remember only three specific cases. One is the turbulent flow through pipe, another is the laminar flow through flat plate, right. For turbulent flow through flat plate NUX, you see, equal to 0.0296 into Rex to the power 4 by 5 into Prandtl number to the power 1/3. However, it is valid for Prandtl number less than 60 and greater than 0.6. Okay. And for laminar flow, we have equivalent Siddharth-Tate equation for laminar flow as well. So here RE is less than 2100 in pipe. So what is the equation? H into D divided by K, 1.86 into Reynolds number into Prandtl number into D by L whole to the power 1/3 into phi u. Phi u is the viscosity correction factor, and you see this 1.8, this group is nothing but Grade's number, right. So that's the equation, Siddharth-Tate equation for this laminar flow. So here this Prandtl number validity range, the upper limit is same as Siddharth-Tate, here is 0.48. Now mu by mu W, it has got a limit, this you do not have to remember actually, only remember this Prandtl number range for laminar and turbulent flow and Reynolds number range. 9.75 greater than 0.0044, right, and overall the Grade's number should be greater than 10 to the power 8. So anyway, so that's all about this. I have also listed some other equations like flow past a sphere, there is a big equation, and what you try to prove that nu is equal to 2 for heat transfer in sphere in a stagnant fluid. So, this is simply conduction in spherical geometry, but we have to solve this temperature profile. How we can solve it? See, you take a sphere, this is a radius r, here we choose a radial coordinate. So, you solve this conduction equation, right, in the fluid region, not within the solid. So, sphere has got a temperature Ts. So, once you go for solving the temperature profile as a function of r for small r greater than capital R, then evaluate minus of k dt dr at r is equal to capital R and equate it as h into Ts minus T infinity, right. So, from here you can prove this Nusselt number equal to 2 in case of sphere or the heat transfer from a sphere in a stagnant fluid. Now, another very important concept I would just like to discuss So, another very important concept what I would like to discuss is the thermal entry length or thermal entrance length. It is very similar, this thermal entrance length similar to hydrodynamic entrance length. So, you see a pipe, we have uniform flow approaching that, uniform flow of velocity u infinity and temperature T infinity. The pipe has got a surface temperature Ts greater than T infinity. So, here the velocity, this temperature profile will be something like this. Here the temperature will be higher, right, then T infinity and then again Ts, right. So, this penetration will further increase and finally, it will be all symmetric. So, this thermal boundary layer here, then here and finally here. So, if I join this, and beyond that, see if this length is LET, right, and this is Z direction. So, Z less than LET, we have developing thermal profile, del T del Z is, del T del Z is not equal to 0. For Z greater than equal to LET, the thermal entrance length, this del T del Z will be equal to 0. So, thermal entrance length is necessary from the pipe inlet to have the full grown temperature profile for the specific flow, right. Very similar to hydrodynamic one. Now, you see that at any point we have delta T. Similar, we can have the hydrodynamic boundary layer, right, and this is, let us say it is LEH, right. So, this is delta. Now, we can write approximate order analysis that LEH by LET it will follow an inverse order of delta. Why? Because if delta, the respective delta is high, the corresponding entrance length will be low. So you can write, and both are in length dimension, so we can write that this will be delta T by delta, and delta T by delta is what? 1 by Prandtl number. Right. So thermal entry length LET will be equal to Prandtl number into hydrodynamic entry length. For laminar flow, you see LET will be nearly equal to, and actually truly we should write this Prandtl number into this 0.6 into Reynolds number into this diameter, right. So thermal entry length divided by diameter is close to 0.6 into Reynolds number into Prandtl number. So basically the thing is, this understanding is very important, that or LET will be by LEH is in the order of Prandtl number. Now for the Prandtl number or Prandtl number to the power 1/3. So we know for water, oil, light organics, the conventional case is that LET, this Prandtl number is higher than 1. So LET is greater than LEH, right. Thermally it will develop much later compared to the hydrodynamic entrance length. On the other hand, for liquid metal, this was a gate question. Prandtl number is much lower than 1. So LET will be much lower than LEH. So the flow profile, the hydrodynamics will go on developing at much later stage. However, thermally the flow will develop much earlier, or means at a distance much closer to that entry. So that's the idea of entrance length, very similar to hydrodynamic entrance length, but we have to know the relationship, the mutual dependence of this thermal entrance length and the hydrodynamic entrance length, and that's actually it's facilitated via Prandtl number. So in the next session we are going to discuss about the heat transfer analogies, and we will move to the understanding of the concept of overall heat transfer coefficient, and will derive the very well known convection equation that Q equal to UA LMTD. Why the logarithmic driving force is important for this heat exchange in a double pipe or in a shell and tube heat exchanger. Thank you.